Hello, welcome to Tennessee's at-home learning series for math. This lesson is for all our 8th graders out there, though all students are welcome to tune in. This lesson is the 10th in our series. My name is Candace Thompson, and I'm an 8th grade math teacher at Oakland Middle School in the Rutherford County School System. I'm so excited to be your teacher for this lesson. Welcome to my virtual classroom. If you didn't see our previous lesson, you can find it on the Tennessee Department of Education's website that I have pulled up for you here. You can still tune into today's lesson if you haven't seen any of our others, but it might be more fun if you first go back and watch our other lessons, since we'll be talking about things we learned previously. Today, we will be learning using functions to model linear relationships in mathematics. Before we get started, to participate fully in our lesson today, you will need the following: paper, pencil, and a hard surface to write on. A calculator is not required, but it may be used to check your calculations. Optional but helpful material would be graph paper. Okay, let's begin. Welcome to the 10th lesson in this series. If you've completed all 9 previous lessons, congratulations. That was a big accomplishment. This lesson focuses on modeling linear relationships, but our first problem will use Fahrenheit and Celsius. The Celsius scale was introduced in the mid-1700s by Andreas Celsius and is a metric measure of temperature. The Fahrenheit scale was introduced in 1724 by Daniel Gabriel Fahrenheit. In the United States, temperatures are usually reported in degrees Fahrenheit, but most other countries use degrees Celsius. The only value for which the temperatures are the same is 240 degrees. Are you ready to look at the first problem? Okay, let's get started. So you've learned in science class that Celsius and Fahrenheit are 2 different scales for measuring temperature. So let's look at what those are. So the freezing point of water is going to be 0 degrees Celsius or 32 degrees Fahrenheit. The boiling point of water is going to be 100 degrees Celsius or 212 degrees Fahrenheit. Let's think about how we would use this information to write an equation that shows the temperature in degrees Fahrenheit as a function of the temperature in degrees Celsius. So we want to use this information to write an equation that shows the temperature in degrees Fahrenheit as a function of the temperature in degrees Celsius. Are the Celsius temperatures the input value or the output value? So the Celsius temperatures are going to be our input value. Remember, when we write this statement as a function of, we are going to have this be our y variable, or our output is a function of our x variable, or our input. To write our equation, we're going to use these points: 0, 32, and 100, 212. The initial value is 32. Here's what the rate of change would look like. So we are going to use the slope formula to find the rate of change. So I'm going to label this x1, y1, x2, y2, and I'm going to use our formula y2 minus y1 over x2 minus x1. So my y2 value is 212. My y1 value is 32. My x2 value is 100. And my x1 value is 0. So I get 180 over 100, which simplifies to 9/5. So my rate of change, or my slope, is 9/5. Okay, let's take a look at this graph. What is the equation of the function shown by the graph? To plot your line on the graph, let's use these points. And remember, I always say that it's 2 points that go perfectly through the grid. So I'm going to use -5, 5 here. And I'm going to use -1, -1 here. So we've got a couple different ways that we can find the slope or the rate of change of this line. First, if you're using a graph, you find 2 points that go perfectly through the grid or hit integer values exactly. You can use this by calculating rise over run. Now, if you do use that method, I would encourage you to first pay attention at each axis and how it is labeled. So that way, when you're counting by the same increments. So it looks like each unit is 1. So I'm going to calculate the rise over run. So I rise 1, 2, 3. Excuse me. Let's try that again. 1, 2, 3, 4, 5, 6. So I rise 6. I run 1, 2, 3, 4. I run 4. Now, one thing I always encourage my students to do if they're using a line is I say use the name test. So my name is Miss Thompson, so I'm going to write my name on this line. And as you see, my name is going downward. So that means that my slope is a negative 6/4, which simplifies to -3/2. So that's one way visually to use a graph to find the slope. Another way is to use our slope formula, y2 minus y1 over x2 minus x1. So I'll go ahead and label these x1, y1, x2, y2. So I'm going to plug in +5 for y2. I'm going to plug in -1 for y1. Be careful here, we're subtracting a negative. Going to plug in x2, which is -5, and then -1 here. And when I do that, I get 6 over -4, which again simplifies to -3/2. So I get the same value I did, which you should. Those are just 2 different ways for us to find the rate of change. So now we found the slope or the rate of change. We have at least 1 point. So we're going to use this information to figure out the y-intercept. With a graph, you can look, but if you notice, it's kind of hard to read. So we want to make sure we get the exact answer. So we're going to plug in what we know into slope-intercept form. So I'm just going to use 1 point. I'll use -1, -1. So my y value is -1. My slope or my rate of change is -3/2. The x value when the y value is -1 is -1. And then plus b. That simplifies to -1 equals -3/2 plus b. Excuse me, that should be positive. Negative times a negative, that should be a positive. That was my fault. Don't make that careless error. And then I get that my y-intercept is -5/2. So the solution, if I were to write an equation for this line, is y equals -3/2 x minus 5/2. Now notice that's -5/2 is kind of hard to see on that line. So that's why this is a great method to find your y-intercept. if you can't see it visually. All right, so let's move on to looking at finding the rate of change in initial value and interpreting that in a variety of contexts. Here is our next problem. So it says, Lily uses some birthday money to open a bank account. Then she deposits the same amount into the account each week. The equation y equals 35x plus 100 represents the total amount in the account after x weeks. What does the initial value of the function represent? Look at these possible answers. Which do you think it is? So I want to know, what does the initial value represent? Look at these possible answers. Take a moment to choose your answer and then think about a reason for your response. Think about how much Lily uses to open the bank account and how much she deposits each week. Which answer do you think is correct? Is it A? That's a good guess, but let's look again at the initial value of the function. The initial value is the amount in the account after 0 weeks, which is the amount used to open the account. This would mean that B is the correct answer, because the answer A describes our rate of change for the function. The answer C is going to be the value of y when x is 1, because it says after the first week. And answer D is the value y after x weeks. Now let's look at finding the rate of change and initial value of a linear function using a graph. If you have some graphing paper, you can use it for this next problem. I actually got my graphing paper off of Math Aid, so that could be a resource that you use for this. Okay, so let's even that up. All right, let's plot the points 4, 5, and 8, 7. So 4, 5, and 8, 7. So we are going to now use a straight edge, or you can just use your paper if you want to draw a line between them. I'm not going to draw any further for the y-intercept. I'm going to wait. Okay. So how can we use this graph to find the slope of this line? How can we use this graph to find the slope of this line? So there are a couple ways. Remember, you can do it algebraically since you have 2 points and plug it into our formula. Or you can just calculate the rise over run between them. So I pay attention. My axes are both numbered. Each unit represents 1. So that's how I'll count when I'm calculating the rise over run. I'm going to rise 2. I'm going to run 1, 2, 3, 4. And if I wrote my name on this line, it would look like it is going upward. So the slope of this line, or the rate of change, would be what? It would be 1/2. So I'll write that information down here. M equals 1/2. Okay, so now how can we use the slope of this line to identify the y-intercept? Now notice I didn't draw my line any further because I was only given these 2 points. I wasn't 100% sure where this line would hit the y-axis. So I can use my slope to work my way back to the y-axis. I see that my vertical shift needs to be 2 and my horizontal shift needs to be 4. So I'm going to work that way until I get to the y-axis. So I'll go down 2, 1, 2. I'll go over 4, 1, 2, 3, 4. And if you notice, I reach 0, 3. Now, going back a little bit, I said that my slope was 1/2 because I simplified 2 over 4. So notice that even if I go by 2 over 4 until I get to the y-axis, or if I go by the simplified slope, 1 over 2, I'm still going to arrive at the same spot. But let's just double check that. So instead of going down 2 over 4, let's go down 1 over 2 until we get to our y-axis. And as you notice, I land on the same spot. So what is the y-intercept of this line? I'm going to connect these completely. What is the y-intercept of this line? That's right, it's 3. How does the y-intercept of this line relate to the initial value for the related linear function? How does the y-intercept of this line relate to the initial value for the related linear function? Good job, it has the same value. So what is the equation for the linear function modeled by the line now that we have identified the slope and the y-intercept? Good, it would be y equals 1/2 x plus 3. What are some real life examples of that you could use this function of this equation to represent? For example, we could say a spider starts 3 meters off of the ground and it climbs up a wall 1 meter every 2 minutes. That's kind of a creepy example, but we could use that example. So this function gives its height in meters, y, as a function of the number of minutes, x. So it gives its height in meters as a function of the number of minutes. And that's just one real world example that you could relate this function to. Can you think of any other examples? Go ahead and write those down. Okay, let's think of a couple more. Here's a shorter one first. Let's just think through this. So the equation 0.15x plus 0.40 represents the cost of mailing a letter weighing 1 ounce or more. In the equation, which part of that description is represented by x? If you said that x represents the weight of the letter, then you are correct. Now, what would y represent? If you said that y represents the total cost of mailing the letter, then you are correct. Now, using the phrase is a function of, how would you state this scenario? Think about it for a quick second. So remember, we always say the variable y, or the total cost, is a function of the variable x, or the weight of the letter. So if you stated this scenario like this, then you are on target. I think you guys are getting the hang of this. Now, let's review one more problem. This time, we're going to use a distance and time graph. Let's take a look and see what you can infer from this graph. See if you can identify the following things. I'll write them out for you. Can you find the initial value or y-intercept? Can you tell me at least 2 ordered pairs on the line? And can you tell me the rate of change? I'll give you some time to see if you can identify these 3 things: an initial value or y-intercept, 2 ordered pairs, and the rate of change. Take some time to do that on your own. Okay, now I'm going to point some things on the graph and check your thinking with mine. So if I'm looking for the initial value or y-intercept, the position on the y-intercept, visually estimating, looks like it would be about 150, knowing that this is at 300. There are several individual points of ordered pairs that we can identify on this graph. So we see that one of them is 300. We see another one is at 500. Do you see any others that you could use? I did too. I saw this one at 200. And then I saw one at 400. So we've got quite a few points here that go perfectly through the grid or that hit at exact integers, but we're a little uncertain of what this y-intercept was. So remember that any of these 2 ordered pairs can be used to find the rate of change by calculation, or you could just visualize your rise over run. Let's see if we can create the equation that models this distance and time graph. We should have enough information to use everything we've learned this week. I'm going to give you a few minutes to start working. Remember that you need to find the rate of change. Now, this is the final equation that I came up with. Y equals 50x plus 150. Did you get the same? If you didn't, let's go back and check your arithmetic. If you did, then great. I'll walk through the steps now. Let's start with finding the rate of change or the slope. I'm going to use ordered pairs that I saw first, which was at 300 and 500. So remember that the slope is the change in y values or the rise over the change in x values or the run. So I rise from 300 to 500, which would be a grand total of 200. And I run from 3 to 7, which would be 4. So my rise is 200 and my run is 4, and that simplifies to 50. Now remember, I'm not going to go through all of this, but you could have also used our formula y2 minus y1 over x2 minus x1 with any of these points that we identified. So now we're going to use this information to figure out the initial value. Remember earlier we said we think it's 150, but we want to make sure, since graphs are sometimes more difficult to read for individual ordered pairs. So we're going to start with our equation, y equals mx plus b, and I'm going to substitute in the rate of change in one ordered pair. Remember, you can use any one of the ordered pairs that you identified previously. It should not make any difference in the final result because they're all on the same line. So I'm going to use the pair 1, 200 to sub in to find the initial value. So my y value is 200. My y-intercept, or my rate of change, or my slope, is 50. And then my x value in y is 200 is 1. And I'm going to use that to find my initial value, or y-intercept. When I do, I have 200 equals 50 plus our unknown. So what plus 50 gives me 200? That is correct, 150. Therefore, the final equation that models this distance time graph is y equals 50x plus 150. You are really getting this. Keep going with some independent practice and review from the whole week. So after this lesson, again, feel free to get on our website here, and underneath the grade 8 lesson 10 lesson in the student packet, there are some additional problems that you can work on. I enjoyed reviewing using functions to model linear relationships in mathematics with you today. Thank you so much for inviting me into your home. I look forward to seeing you in our next lesson in Tennessee's At Home Learning Series. Goodbye.